Now, you guys may have noticed that there's been an awful lot about energy in the news of late, and in particular, there are two things that have been very topical, and that is the price of gas and also the perception that we have a gas shortage in Australia. So let's have a look at price first. This is the monthly average wholesale gas price, and you can see that over time, this graph starts in July 2014, you can see that over time there's been a reasonably gradual increase in price through this period, but then when we get to April 2016, you can see there's this very sharp jump in price, almost a doubling in price in some states. On the shortage side of things, this really came to the media's attention in March this year when the Australian Energy Market Operator released their gas statement of opportunities report, and this graph is in that report. And what it shows us is on the x-axis we can see time, and on the y-axis we can see how much supply is going to be able to be brought to bear during that time. And this hashed line across the top here tells us what Australia's domestic consumption requirements are going to be. And it's this little innocuous white sliver here that has caused all of the drama, and that is where they are forecasting there was going to be a gas shortage. Now, they have actually revised this forecast since then. When they released their June update, that shortage no longer appears. But despite this, the situation with prices and perceived shortages was suitably severe that the government decided to step in and implement some responses to those things, and one of those was the Australian Domestic Gas Security Mechanism, and we can expect some announcements on that front from our new Minister in the next few days, I believe. So all of those, the pricing and the gas shortage, do not arise overnight. They're based on much longer term trends. So let's have a look at some of those underlying trends now. So starting on the demand side first, here you can see Australia's domestic consumption through time, starting in the mid-1970s, and you can see that there's been a fairly steady increase in our gas consumption through time. It's a little bit variable by state. You can see here in the green, Victoria, a slight increase but generally pretty static, and up here in the orange, Western Australia though, they've seen much more marked increases. Now it's one thing to say what our consumption has looked like previously, it's quite another to try and forecast what our consumption is going to look like into the future, and then particularly at the moment, because there's a lot of uncertainty around what's going to happen in terms of is Australia going to adopt a low emissions policy framework. If we have a look on the, sorry I missed a bit, but of course domestic consumption really is a small part of the pie. A large proportion of where the demand is coming from for Australian gas is actually exports, and here we can see Australia's LNG volume through time, and you can see starting in about 2003 we have quite a steep progression, and then we hit 2014, it really goes off the charts. Now the question arises is, given that we think we may have increasing demand for gas consumption domestically, and we also know we're going to have increasing demand for gas to go to export, it is, can we produce enough to actually meet those demands? So if we switch sides now and have a look at the supply side of things, this is Australia's production of gas through time, and the red line we can see across the top here is our total production, and you can also see that those bars are broken down into how much of our production is going to domestic consumption, which is the blue, and we can also see the amount of our production that is going to export. And you can see that the proportion of our gas going to export has been increasing through time, and by the end of this graph, ooh, that was unexpected. There we go, try the right button. We can see that by the end of this graph in 2015, our exports are consuming nearly 50% of our production. Now if we extend that graph in time a bit, to 2019, we can see that our proportion is only going to increase further, and this is when we predict that the new LNG export terminals, Wheatstone, Prelude and Ichthys, will be getting going, and there'll be something approaching full capacity by then, and by the time we get to the end of 2019, we'll be running at something like 65% of our gas production will be going to export. Now this massive spike here, well, it is very good for making excellent headlines like Australia will become the world's greatest LNG exporter. It doesn't actually have that much impact on the domestic market, and that's because the gas that's going to supply those LNG trains is coming off the northwest shelf, and it was never destined for the domestic market. Something that is going to impact, or has impacted, sorry, past tense, on the domestic market was when Queensland exports started at the very beginning of 2015, and that's because the gas that feeds the Queensland exports comes from onshore gas, and that gas has previously been dedicated to the domestic market. So when those Queensland exports kicked off, that gas that had previously been in the domestic market was now removed, and that caused a tightening of supply. Initially that was in Queensland, but then as time has gone on and the LNG exporters have needed to harness more supply to meet their contractual obligations, they've also been sourcing gas from other basins in other states. So it's caused a broadening of that tightening of supply. Now if we pull together those supply and demand factors into one statement, we can get a feel for what the state of the domestic market is, and the Australian Energy Market Operator have done a really good job of that in June, their June 2017 update, and we can see that in their opinion domestic gas and supply in Australia remain very finely balanced, and the two key things that they've identified about whether we are going to have sufficient supply is whether how much gas we're going to have remaining after exports have been accounted for, and also the level of domestic gas that's going to be required for the generation of electricity using gas-fired power plants. So the question remains is, given the domestic market is reasonably tight on the supply side, can the development of onshore gas, and in particular unconventional gas, be part of the solution to any of these potential supply shortfalls in the future? And you would think that fairly unequivocally the answer to that would be yes, but there are a lot of development hurdles for companies to get over before they can bring gas to market, and we can see a list of those here. The first one is the fact that our geological understanding of these resources is still quite immature. They're a new sort of resource in Australia. We haven't done much development of them, so there's a lot more learning that needs to be done in that space. Likewise, on the technology side, most of the drilling techniques we use for extracting shale gas come from the US, and because our shales are not direct carbon copies of US shales, they need to adapt those drilling methodologies to cope with the Australian context. This third one here is rather topical in a media sense, and the social licence around unconventional resources is a little bit dubious. Some of the issues that are in the space include the perception of using prime agricultural land for unconventional resources development, issues around water also, and obviously issues around fracking. Access to infrastructure is another key impediment to companies, and in particular pipelines. We can see a map here on the right of the East Coast pipeline network from the ACCC's report, and one of the key issues we have is having enough pipelines in the right place to allow companies to get their gas to market, and as a result of some of those issues, we're currently building a new pipeline from Tennant Creek to Mount Isa. Well, Gemina is actually, I won't say we. And that will improve the connectivity of the market from the Northern Territory to the East Coast. Obviously there is a lot more work that needs to be done on that space though. On the investment side now, the uncertainty around policy settings is proving a little bit of a challenge in terms of attracting investment. Companies need to be very confident that they're going to have a market for their gas to go into before their investors will be prepared to commit the money, so they're struggling a bit on that side. And the last one is definitely been in the media an awful lot, and that is around legislation, and this is where the state-based fracking and unconventional exploration moratoria and bans fit in. Now on that fracking and exploration moratoria front, before we can understand why fracking is such an issue, first we need to understand the actual resources themselves. So if we look at the schematic here, we can see some unconventional resources in the pinky browny colours down the bottom. We can also see some conventional resources up here. So we have a conventional trap here, a structural one, and another conventional one here in a stratigraphic style trap. Now the two key differences when it comes to developing an unconventional resources as compared to a conventional resource, that is when we drill a hole into a conventional resource, we expect we would naturally get quite a high flow of gas to the surface, or oil in that case. But when we drill a well into an unconventional resource, we don't get very much natural flow of gas to the surface, so we need to do something to encourage that flow of gas, and that something is hydraulic stimulation, or in common parlance, fracking. Now the other thing that is often perceived negatively when it comes to developing an unconventional resource is the sheer number of wells that are required to develop the resource. You can see that an unconventional resource occupies a lot more space laterally than a conventional one, so the wells that are going to be required to develop that resource need to be a lot more widespread, and because of the flow impediments mentioned previously with regards to fracking, there also needs to be a lot more of them. So given all of those potential issues associated with developing these resources, how are we best going to go about developing them in the national interest? Now one of the best ways we can do this as a geoscience agency is to ensure that the people who are making the decisions, and in particular our government stakeholders, have the best quality information they can possibly have to make clear, unbiased decisions. And one of the ways that has been identified as a good way to do that by the Australian Council of Learned Academies in 2013 is to conduct a national unconventional resource assessment, and you can see their quote there. Now, where does GA fit into that space? Obviously we don't work at the development end of the spectrum, that is entirely in industry's hands. Rather we work at the other end of the development spectrum, and that is in understanding the resources in the first place. So in 2014 we commissioned the Unconventional Resource Assessment Project to get a better understanding of our unconventional resources in Australia. Now some of you may know that there have been assessments conducted previously in Australia, and you can see a list of those here. We have faced quite a lot of questioning about why we would consider doing any more, and there's a few reasons for that. The first of these is to ensure that we can provide complete transparency in terms of the data that's gone into the assessments, how we've done the method, and also how we should be interpreting the results, and we just don't get that from those previous assessments. Another reason why we would consider doing more assessment is to evaluate a broader range of resources. These previous assessments have focused primarily on shale gas, a little bit on shale liquids, but primarily on shale gas. And in deciding to do another round of resource assessments, we had the opportunity to look harder at shale liquids, but also to assess tight gas, and that has never been assessed previously. The third point here is to enable the use of the newest possible data. If you see some of the years of completion for some of these previous assessments, plural, 5 years is a really long time when it comes to a newly developing industry. So between 2011, when the Energy Information Administration first completed their assessment, and now there's been a lot of Australian specific exploration data become available. So we really wanted to leverage that data and incorporate it in the assessments. And the last one here is important, and that is that we should enable the government to have its own independent viewpoint on these matters. So now we've decided we're actually going to do some assessments. We need to make some decisions about how we're going to do the assessments, and we've decided to use a volumetric approach, and in particular a modern day hydrocarbon saturation kind of approach. Now that's just a really flash way of saying, given a volume of shale or tight gas reservoir, how much gas or oil is sitting in that reservoir today? We also needed to make some decisions around whether we were going to use a deterministic approach or a probabilistic approach, and when we do a deterministic calculation, we only do a single calculation, and we always only use one value per input parameter. Whereas when we do a probabilistic approach, we use multiple values for each input parameter, and we also do multiple calculations. So if we look at what that looks like schematically, this might be one of our input data sets. If we were just going to use a single value to try and represent that data set, we might choose this one, or we might choose this one. But the reality is, any single value will not do a very good job of representing that data set. When we do a probabilistic calculation, we use many values to represent that input data set, so we get a much better representation of those input data sets, and that enables us to do a much more rigorous calculation. So in summary, we've done a probabilistic volumetric approach, and what that gives us is a gas in place and an oil in place number for each resource. Now a gas in place number just tells us how much gas is going to be in the ground. It doesn't tell us anything about how much of that gas is going to be able to be extracted or what the economics are around what that extraction might look like. We need to do that in another way, and we do that by incorporating a recovery factor. And recovery factors trying to, depending on how we use them, they try and capture a multitude of things. Our recovery factor represents geological things. For example, what is the mineralogy of the shale that we are looking at? Is it amenable to being fracked? And those kinds of things. We also capture technological factors, and that is primarily about drilling technologies. Now recovery factors vary quite a lot between assessments. They also vary a lot between different resource types. You can see here different numbers for shale oil and shale gas as used by the Energy Information Administration, and they also vary by region. So we've decided to use a very conservative recovery factor, and that is 5%. It's also a flat recovery factor. We haven't varied it between plays. And the reason we've done this is because the unconventional resource industry in Australia is very new. We don't have very good understanding of the geology, and we don't have very good understanding of the technology that's going to be required to get that gas and oil out of the ground. So best to be conservative at this point. So once we've decided on the methodological things, we needed to make some decisions about which basins and which formations we were going to have a look at. And we set up some selection criteria to do that, and you can see those listed up here. And of course, obviously geology was very important. We used industry activity as a bit of a proxy for what they were thinking was going to be viable. This perceived viability and size of prize parameter really is just a way of us thinking about if it's only a very small basin and there's only one formation in it, that could potentially be prospective, and so the potential size of that prize is only going to be quite small. Maybe we won't put that first on the priority list, maybe we'll focus on the bigger ones first. Data availability was a very important consideration. We need a particular suite of data to do these assessments, and if we don't have that data available, obviously we can't do a very good job. We did a little bit of consultation with our state survey counterparts, and this last one proved to be unexpectedly important, and that is we wanted to choose basins and formations that were going to be able to best inform policy decision-making processes at that particular time. So in year one, once we'd done our selection criteria assessment, we ended up with a list that looks like this. By the time we got to year three, you will notice the somewhat conspicuous inclusion of a couple of Victorian basins. So all in all, we assessed 5 basins, and within those 5 basins we've completed 13 shale and 8 tight resource assessments. So let's switch gear a little bit now and have a look at the method. So we'll have a look at the shale gas method first, and you can see there it's a product of how much free gas in place there is and how much adsorbed gas there is in place. So we look at a very close-up shot of a shale. We can see the brown blobs there are kerogens, and the free gas is the gas that's hosted in the pore space between those kerogens. The adsorbed gas is the gas that adheres to the surface of the kerogen themselves, so they're actually bound onto the rock surface. Now this is the calculation we do for the free gas part of the process. Let's simplify that a little bit. The A times H here is used to tell us how much of the formation is going to consist of organically rich shales, and this concentration factor here tells us how much gas is there in those pore spaces in the rock, and our BG on the bottom half of the equation there is just a conversion factor. The adsorbed gas calculation is even easier. It's just the gas contained times the density of the shale. So let's have a look at how that method actually works in practice. You can see here we've got a basin. All those blue dots are where wells have penetrated one particular formation. And the first thing we need to do is draw a line around the full formation extent. And if we do that, it might look something like this. The next thing we need to do is take a subset of that to meet these criteria here. And these criteria have been imposed to ensure that there's a chance of overpressure being present in the shales, and that will help with extractability later. And there's also the 5,000 metres cut-off and the 15 metres minimum thickness cut-off have been applied to ensure there's some chance of that, volume of rock being economically viable to do extraction from. So if we do that, we end up with these pink polygons here. And the last step we need to do mapping-wise is to look at how much of that area in the pink polygons is going to have the potential to host organically rich shale. And we do that using the average total organic content analyses from the shales themselves, and you can see the green dots there represent places where the total organic content is more than 2 weight%, and the red dots represent where it's less than 2 weight%. So we draw some lines around those green dots and we end up with the final prospective areas, and you can see those there. Now we need to move on to calculating the thickness part of the calculation, and we do that using well data, and these numbers represent how many wells we have available for these particular prospective area polygons. You can see the number of wells we have to deal with is quite variable. And when we go to calculate those thicknesses, we don't actually just want the full thickness of the formation, we actually want the thickness of the formation that's going to be prone to producing oil and the thickness of the formation that's going to be prone to be producing gas. And we can see how this works here. These 10 wells are actually the 10 wells here from this prospective area polygon. And you can see in these wells at the top, they're relatively shallower wells, and they're only going to be inclined to produce oil from those shales. But when we get down here to Valentine, it's a bit deeper and the formation is a bit thicker, and we're going to end up in a stacked play situation where we end up with oil and wet gas coming out of that same well. And in Yarrada, here at the bottom, we're going to end up with wet gas and dry gas. And if we just take a second to visualise that schematically, it looks like this. So within this single prospective area, we're going to end up with some shales able to produce oil and some shales able to produce gas. So this is the last geological part of the calculation, and this is where we find out how much of the formation actually consists of shale. And we do that using the net shale ratio, and this is a very simple calculation, if you like, evaluation maybe. So this is a well log, a little snippet of a well log, and we can see what we want is how much of the formation in that well consists of shale, and that's this piece here. We know that shale is 40 metres thick, and to calculate the net shale ratio, it's just 40 out of the full thickness of the formation, which is 65 metres, and that gives us 0.62. And we do these net shale ratio calculation for a number of wells in each prospective area. So now we've actually done all the geological parts of the free gas equation. We can see these here. We've got a prospective area. We know what the thickness of the formation that we're interested in is going to be, and we know what the net shale ratio is going to be. Now we need to have a look at the petrophysical side of things, and that tells us, we use that kind of data to look at this concentration part of the free gas equation, BG, and also the adsorbed gas in place equation. Now this petrophysical data is measured data. It's done using core samples from wells, and in lots of instances where we have measured data, we can just use that measured data directly. But when we're in the position we don't have any measured data available, we have to make some assumptions, get that out, and we do those assumptions by looking at the geology and deciding what looks reasonable for those particular shales. So now we come to the probabilistic part of the process, and I mentioned previously that when we do probabilistic calculations we use multiple values for each input parameter and we do multiple calculations. So I'll just explain a little bit further how that works here. Probabilistic calculations are something that gets talked about a lot, but no one ever actually explains how it works. So I'm going to spend a minute just showing you how it works. So if we can imagine we've got 3 input data sets, and we've taken the raw data and we've fitted a distribution curve over the top of that. So now it looks like a probability distribution. then we need to move on to actually doing the calculation. In this instance, this is just an example. This is the prospective volume calculation. So when we start calculating, we use a particular software that's able to do probabilistic calculations. And what that software does is it goes and it looks at your input distributions and it says, I'm going to randomly choose a value from each of those input distributions. And then I'm going to do the first one of the calculations. So it does that calculation successfully, goes back to those input distribution, randomly chooses another value from each of those distributions and does the second calculation. And so on and so forth until it reaches the number of calculations that you've asked it to do. And we've asked at risk to do 10,000 calculations for these resource assessments. Now, you might be wondering how we actually deal with having 10,000 answers to the equation. And the way we do that is by aggregating them. And what the software does is it plots them on a cumulative frequency histogram. So for example, this bar might represent how many times of those 10,000 answers was your answer between 200 and 250, just for example. The software then fits a probability curve over the top of that, and it also gives us some numbers, and we get all of the usual statistics, mean, median, mode, kurtosis, etc. And we also get these P numbers. So if we plot those P numbers on the graph here, we can see them there, P90, P50 and P10. If I was to explain in words what these numbers actually mean, when we look at a P90 value, it's saying at this point, or at this value rather, there is a 90% probability that your gas in place resource is going to exceed that particular value. And if we look at the flip side of that, which is P10, at this value here, there is only a 10% probability your gas in place resource is going to exceed that value. So they give us some feel for what the uncertainty in the assessment is like. And the last thing we do in the calculation is apply that recovery factor. And we apply that recovery factor to the median value here, P50. So that was the shale gas method. The tight gas method is very, very similar to the free gas part of the shale method. So there's lots of similarities. The depth thresholds are exactly the same. The primary difference is that this time, instead of trying to map the extent of organically rich shales, this time we're trying to map the extent of tight reservoirs that have the potential to be oil or gas saturated. One of the key ways we do that is by applying the net sand ratio, and you can see it's actually the inverse of the net shale ratio. So it tells us how much sand is in that formation, and then we also apply the net pay interval, and that tells us how much of that sand is actually going to be an effective tight gas reservoir. And those are the values that go forward into the calculation. So if we have a look at some results now, and you will notice I'm going to flick through these results very quickly. There's a lot of them, and we don't have time to delve into the intimate details to do with the geology. What we will do is present them in the order of where we had the most data available, which was definitely the Cooper Basin, to the end where we had the least data available, and that's definitely the Canning Basin. And we'll give some comment on how that has affected the outcome as we go. So starting with the Cooper, you can see here there's an awful lot of gas fields and oil fields also up here, and that tells us that there's a lot of data available. The data that is available for the Cooper Basin has also been particularly well compiled at the moment because Lisa Hall has just finished her Cooper Basin prospectivity study and built a beautiful model as part of that, so we've got a chance to use that model in our resource assessment process. Now if we look at the formations we assessed two shales, the Roseneath and the Murderee, and we also looked at 4 tight gas plays, and that's the Talachi, Daralingi, Epsilon and Patchawarra formations. So this is what the prospective area maps look like when we have lots and lots of data available in a 3D model. You can see here the pale green is where we're likely to get oil, the dark green is where we're likely to encounter wet gas, and the red is where we're likely to encounter dry gas. And if you look at what the numbers are for those 2 shales, we can see them here, quite similar in terms of order of magnitude, but a bit more gas in the deeper Murderee shale. If we look at the 4 tight gas results now, key difference here is this is the Patchawarra formation, this one here is the Talachi formation. You can see the extent of these two is significantly more than for the Epsilon and the Daralingi, And also something you can't see as we're presenting this in 2D, that is the Patchawarra and the Tallahatchie are also significantly thicker. And we can see that playing out in the results. The Patchawarra formation result is significantly more than the Epsilon or the Darralingi. So if we add all of those together, we end up with just about 58 TCF of gas that we can expect to be recoverable and just about 25 billion barrels of oil. So if we switch over to the west coast now, to Western Australia and the northern Perth Basin, you can see the number of fields here. Most of those are producing. I think there's 9 producing fields in the Perth Basin at the moment. The onshore Perth Basin, I should make that distinction. So there's quite a lot of data available for the Perth, and Lucci somehow, I'm not quite entirely sure how, he found the time to build some 3D surfaces for the Perth Basin, so we've effectively done a 3D modelled based assessment for this basin. Now we only looked at 2 formations in the Perth Basin, the Cockatier Shale and the Karanginia Formation, and we can see their prospective area maps here. Again, this part of the formation is likely to produce oil, this part of the formation is likely to produce wet gas, and we'd expect to see just about 6 TCF of recoverable gas there and 2 billion barrels of oil. We look at the Karanginia Formation, which is deeper in the succession, still a little bit of oil around the edges, but much more wet gas, and then in the very deepest part of the basin we would also expect to find some dry gas. So if we add all of those together, we would expect about 11 TCF of recoverable gas and 3 billion barrels of recoverable oil. Now if we head over back to the east coast again, to the Gippsland Basin, I shouldn't need any introduction to the Gippsland Basin. It's been a very successful hydrocarbon producing province for a long time. Since the 1960s, in fact, in the offshore when Barracuda was discovered. Now that means there's an awful lot of data available for the offshore, but for the onshore, not been as much exploration done, and certainly not as much successful exploration done, so data is a bit limited. In the Gippsland we did have a 3D model to use though, which was really handy, but in terms of the availability of that petrophysical data and well data, a lot more limited here. Now, because of the nature of the geology in the onshore Gippsland, it's dominated by the Strzelecki group, so we only decided to assess that, but we did do it as a tight gas assessment and a shale gas assessment. And we can see the impact of what that limited well data is having now. You can see the prospective area maps look very different. Now we've got very laterally constrained polygons within which we think there's going to be some resources. And actually this one here, this one is sitting over the Wombat and the Triffin, Gangle and North Sea Spray accumulation, so that worked out fairly fortuitously. And this is the tight gas extent too. So if we add those together, we've got about 19 TCF of recoverable gas and just on 1 billion barrels of recoverable oil. Now we shift just a little bit around the corner on the southern margin to the Otway Basin, and we can see here there's been a lot of successful exploration in the onshore again. This is where the thylacine and Casino, Geograph, etc. fields are located. A little bit of success in the onshore. There's a little cluster of fields that have produced previously here in the Port Campbell embayment, and there's also some accumulations that have produced a little bit of gas up here in the South Australian Penola Trough, including Katnook, etc. Now the Otway Basin is the first of the basins that I've presented here. We'll use exclusively well data to do the assessment. No 3D models here and not a lot of petrophysical data either. So we looked at 3 shales in the Otway Basin, the Umarella, the Crayfish subgroup and the Casterton Formation right down the bottom. And we also did 2 tight gas assessments, the Umarella and the Crayfish subgroup. And if I just click through these in succession, you'll see that as we get deeper in the section, Casterton Formation being at the bottom, go back, you'll see that the extent of the polygons is reducing, and that's because as we get deeper down we have less well penetration, so the prospective area polygons are intrinsically tied to how much well data we have, and the result of when you don't have a lot of well data is that the prospective area polygons get very small. So this is the Umarella tight gas assessment. You can see there's no problem with lateral extent there, and this is the Crayfish subgroup tight gas assessment, and you can see it's mainly located here in the Penola Trough. So if we add all of those bad boys together, we get a total recoverable gas of about 7 TCF and a total recoverable oil of about 1.5 billion barrels. So last but not least, the Canning Basin, definitely the most spatially extensive of all the basins that we've looked at. Exploration in the Canning has been going on for a very long time. We've had some success up here on the Leonard Shelf with the discovery and subsequent production from the Blina field. There's also the Lloyd, Boundary, a few others, can't remember the others, but they're all located up here on the Leonard Shelf. In contrast, down here in the southern part of the basin, exploration has been much more sparse, so there's much less data available here. And as with the Otway Basin previously, no 3D model here and very limited well data as well. Now, we must have been having a rash moment when we decided what to assess in the Canning Basin. We did do 5 shale assessments, and you can see them listed here, and we also did 1 tight gas assessment in the Laurel Formation. So if we just scoot through the shale plays here, starting with the Laurel Formation at the top of the section, Laurel, Devonian Reef Complex, the Malanjeri Formation, which I'll just pause on briefly. You can see the amount of geochemistry data available to define that polygon. If we were going to award a special award for the most degree of uncertainty associated with an assessment, it would definitely be that one right there. Kiribati Group, and probably the most well-known of the formations we have assessed in the Canning, the Goldwater Formation. Now you can see here, particularly with this Kiribati Group number, much higher, given the relatively constrained nature of some of these polygons. What we would expect to recover from those polygons is actually quite high comparatively with other basins, and that's because formations in the Canning Basin are much, much thicker than others that we've assessed previously, so the volumes of recoverable gas and oil we would expect are much higher also. Laurel Formation tight gas play here, restricted to the Fitzroy Trough and surrounds. Brew Energy have done quite a lot of work down here at this end in Lawford 1, and they've decided that in doing that detailed work that the tight gas play doesn't extend that far into the Gregory sub-basin, so we constrained the assessment to just this half of the deeper centre. And you can see there we'd expect about 34 TCF of gas to come out of that Laurel Formation tight gas play. So if we add all of those together, we get a somewhat gigantic number, and a similarly gigantic number on the oil side as well. Now if we take all of those basins worth of assessments and pull it up to the national level now, these numbers here are our total recoverable gas and oil that we think is sitting in those 5 basins. If we add those together to get a total of all of them, we expect to see just about 550 TCF of gas and just about 75 billion barrels of oil, which is a lot. Just to put that in perspective, this number here is Australia's national domestic consumption of gas, 1.3 TCF, and our national consumption of oil, 0.38 billion barrels, is in 2014-15. We do a little bit of maths using those numbers. When we use a 5% recovery factor on the basins we've assessed, that tells us we might have something on the order of 400 plus years of gas supply and 190 odd years of oil supply, just in those 5 basins. Now that is somewhat ludicrous. If we just have a moment where we're even more conservative and we use a 1% recovery factor, we still have more than 80 years worth of gas supply and just about 40 years worth of oil supply. And it pays to remember in this instance that we've only assessed 5 basins. There are a lot more basins in Australia that have potential for unconventional gas. The Beetaloo sub-basin is one of the very well-known ones. This is the Northern Territory Survey's 2017 assessment result. So you can see that while the numbers we have suggested are going to be recoverable are quite large, that is really just a small snippet of what the whole country has to offer. It also pays to remember that when we're talking about the results of our assessment, it only tells us about what the resources in the ground are. It doesn't tell us how much of that can successfully be extracted, and that will only come with time. So, what can we do in the future to improve our knowledge in this space? Some of the geological based things we could do is we could look at other basins. We could also pick up other unconventional resources. For example, we could consider assessing coal seam gas or hydrid plays, get that out. Something that we discovered during the course of the assessment, that the state that your underlying data sets in makes a huge difference to how much you can get done in a given time. So spending some time and effort to improve on those input data sets would be really good. These three here are current databases we host at GA, and there is already some work in train to improve this. This fourth one here would be a new undertaking for us, and that would be to build a national shale rock and our reservoir properties database, and that would be immensely useful. Now, once our underlying data sets are in really good form, we can potentially look at automating the resource assessment process to some degree, and that would be really excellent, because then we can potentially do updates more often and get through a bit more work. Now, this one here, I've mentioned previously, when we do gas in place assessments, you really need to then take the next step, and that is to understand how much of that gas and oil in the ground is going to be recoverable, and there needs to be a lot of work done in that space, and there also needs to be a lot of work done to evaluate what the economics of that's going to look like. There is a possibility that some of this extraction is just not going to be economically viable. And this last one down the bottom here, this is something GA should be doing all the time, and that is to continue to promote our findings to stakeholders. And we want to do that because that allows our stakeholders, and particularly in this instance our government stakeholders, to continue having access to that clear, unbiased data that they need to make decisions. So in conclusion, first one here, there is a possibility that developing Australia's unconventional resources could potentially have a positive impact on the price that we're paying for our gas, and also security of supply. And it would do that just purely by improving the amount of supply available to the market. Over the last couple of years, GA has developed a new capability, and that is to undertake doing unconventional resource assessments. We've completed 5 of those assessments and their associated data releases, and we've done that by using methods which integrate multidisciplinary data sets, and also use reporting that's 100% transparent, which is really important. We've also used predictive methods that quantify uncertainty and also preserve that fundamental data. As I mentioned previously, it's all well and good to have a geological understanding of your resources, but for this industry really to develop, we need to go a bit further, and we really need to get that additional understanding of how recoverable those resources are going to be, and what the economics associated with that extraction are going to look like. I'd just like to take a second to acknowledge all of the fabulous people that have been involved in this process. We wouldn't have been able to get it done without them. And that's it. And if you're going to ask me questions, ask me quick, because this is what my mind is going to be on right now. This is where I'm going on holiday. And that's it. Thank you.